So, hi. How many people are still awake after a whole day of sessions? Excellent. I'm not. If I fall asleep, a gentle nudge in my general direction will help. My name is John Azariah. I work on the Microsoft Quantum team. As part of many initiatives there, I was one of the people that helped design the Q# language, and I currently work with quantum infrastructure. And in fact, the hunt for the qubit is happening in Copenhagen as we speak. So I actually come here quite often with my team. And so it is a pleasure to be at Copenhagen to speak at NDC. So what is quantum? How many people here have actually done anything with quantum computing? Any physicists in the area? OK, good. So that helps because I give conferences all over the place. Some of them are physicists that don't know computing, and some of them are computing people that don't know the physics. And I don't know either, so I'll manage somehow. Yes. Right. So this is the broad outline of the talk, just to give you a sense of how different quantum computing is, why we need it, and so on and so forth. Where we might actually see critical applications, either early on in the phase or later, what it takes to actually build a scalable quantum system, and how you can get started if you're interested in preparing for this revolution. And hopefully, this talk will inspire a seed of thought about perhaps looking at the world a little differently and gaining a better appreciation for nature and how computing and nature are actually quite closely intertwined. So I suspect not very many of us were around at 2500 BC, but it was a bit slow back then. Computation wasn't very fast. You might say that a skilled person there probably could have done a few operations a second, or maybe one operation a second. And in the 20th century, we know how to compute with numbers. And we've gone from an esoteric-based system, like in the abacus or whatever other types of calculation there are, to the fast classical chip. And billion operations a second with a cluster, maybe, right? We have teraflops, so we have something like that. And that's like 6 or 7 or 8 orders of magnitude in terms of maybe 12 orders of magnitude in terms of how fast you are, how much faster you are compared to how you would do it manually. Yeah. Quantum computing is actually a completely different beast. So while Moore's law kind of guides the approach to the 20th and 21st century approaches that we have, the quantumness of it for specific applications can actually speed things up by 10 to the 300. So we have 300 orders of magnitude, significantly improving the kind of computational capability that you have. Obviously, there's some catches to this, and there's limited application and so on. And part of the whole idea of computation is to first, quantum computing is to actually understand that there is not just a shift in terms of just getting faster, but also a shift in the way you think. So this paradigm shift to go from classical to quantum is kind of an important one. So I'll give you an example. So here is the RSA 2048-bit problem. Everyone who has a credit card is very happy that this problem is hard to solve. Because if you can factor this into 2 primes, that would then, when multiplied, give you this number, you could break encryption. Fortunately for us, classically, that takes about 1 billion years. And this is a good thing, right? But that's not the only application of factoring. And so it might be useful to be able to figure out how to factor that number. And it turns out that the quantum solution will actually speed things up considerably. Yes, sorry. The jokes are coming too late at 5 o'clock in the evening here, so you'll have to excuse the opportunity to take the quick shot, right? But the reason why, so there are two messages that informally I want you to take away from this, right? One is, there is a significant speed up that you can get for certain types of problems. But as it will become apparent as we go forward in the talk, the speed up doesn't happen universally. So it's not like because we can now speed things up for this problem, you can now play Tetris any faster, right? So some problems are going to stay the same. Some problems, specific problems, will be improved by using quantum computing. And there's a variability in the kind of speed ups that you get when you have quantum algorithms. This has a very profound impact, as we'll see in a few minutes, in the way in which we think about software development, even. The other thing, of course, is to not be worried about the hype. We are quite some way to getting to the point where we can factor 2048-bit numbers. And we're also quite some way along the way to find algorithms for encryption that are resistant to quantum speedup. So we already have classically proven algorithms that we can use that won't have this kind of a speedup. So we aren't going to necessarily all short Bitcoin anytime soon. Now, why is this? Okay, let me just walk you through what the paradigm shift looks like. So back in 2000, okay, that is a log-log plot. So it's a logarithmic step on the x and the y axis. So at the top of the y-axis is 1 billion years. At the right, you have 100,000 qubits. And somewhere in the red line is where you have the 2048-bit problem. And in 2003, if you can see the yellow on white, sorry, that was more than 1 billion years. And 15 years later, Moore's law pushes that curve to the right. And that is phenomenal in itself, right? We keep doubling and we keep moving things to the side. But on a log-log plot, that curve doesn't move right fast enough for us to be able to use it. The paradigm shift is that a quantum machine doesn't take advantage of Moore's law, and in fact is not limited by Moore's law. And the shift is a different kind of curve altogether. And by speeding the machine up, I beg your pardon, we can actually achieve the kind of speed up that we have promised from this. So there's a paradigm shift in this. It's applicable to a small set of problems. And in this particular case, the particular example that we have isn't unfixable. It's not like we've broken encryption and we can't fix it again. That's the takeaway from this. Cool? Right. Here is the fastest supercomputer in the world. Okay, so the real question is, why would then we consider quantum computing? What's the big deal? What does it do, and why would we use it? This computer is capable of actually doing a chemical analysis of my favorite molecule, right? And when I mean the computation of that, what that means is, if you think about what chemistry is, if you think about how molecules are formed, it's really interference between the electrons of different atoms. And each of those electrons together, when they interact with each other, they form a lowest energy state, which results in a stable molecule. Okay? If you want to think about it mathematically, there's a wave function describing each electron, and the solution of the addition of all the wave functions to a composite wave function, where the energy of that wave function is at the minimum, is what a molecule is. From a mathematical perspective, you need to basically look at each electron in the whole system, figure out all of its combinations with all the other electrons, solve a very large differential equation, find its minimum, and when you do, you know how to describe one of these molecules. Okay? That's the real complexity of the problem. Everything breaks down once you put a metal inside. So this little ligand on the side here has two transition metals, has an iron and has a molybdenum. And to compute the state of that, just that piece of the molecule, would take more than the lifetime of the universe on a classical machine. And that's because the number of electrons now, basically, every time you add an electron to a system, you kind of double the size of the problem. So it's not like I can solve for 20 electrons, so 30 electrons is just a little bit more. 30 electrons actually is 1,000 times more work. And this problem, why do we care about this molecule? I'm going to tell you about that in a minute. But this problem turns out to be very, very important for us. And in some sense, there's a profound observation that you can make when you look at this system. I've described to you that this molecule is the solution to a difficult math problem. And I've posed a second molecule as too difficult to solve, right? But if you've turned the problem on its head a bit, you realize that this molecule exists already. Both the molecules exist in nature. So nature is somehow already doing the mathematics. So there's something about nature that knows how to solve the hard math. So if I take a random problem and find a way to represent it in a way that nature can solve the problem for me, I can now use nature's supercomputing capability to solve hard math problems, right? So that mental paradigm of turning the problem on its head is actually what Richard Feynman proposed in 1950 as, in fact, the basis for quantum computing. Like, he was like, you could use natural quantum mechanical phenomena, like adding electrons, to solve the difficult math problems. And so don't be daunted by the fact that the math problem is too hard. Nature's already solving it, so all you have to do is try and figure out how to flip the problem around and get nature to solve your problem for you. So in some sense, that's actually what we do in a real quantum computer. We take advantage of the quantum mechanical properties of these devices, of these particles that are, we put them in an isolated environment and model the problem in such a way that they represent the solution that we want. And we let the qubit figure out what the solution is from that perspective. So that's kind of what we do. But let's come back to FEMOCO, right? So 1911, before 1911, if you wanted to fertilize fields, you used organic fertilizer or you did crop rotation, right? Crop rotation is like when you grow beans. Any gardeners here? If you grow beans in your plot, they naturally fertilize the soil, right? How does it do that? Well, if you remember what they would have told you in grade school or whatever, it does nitrogen fixation and stuff like that. Well, nitrogen fixation is a really interesting problem. Somehow nitrogen from the atmosphere, which is a very stable molecule, and hydrogen from water, which is also a very stable molecule, trying to get them to break apart and recombine to form ammonia, which is the basis of the nitrogen fixation for fertilizer, happens naturally in a bean plant, right? But it is so important for us as humans that from 1911 till now, we have spent enormous amounts of the human energy budget making ammonia. Ammonia is the single most important industrial chemical on the planet today, and we spend nearly 3% of our human energy output making it so that we can fertilize the grounds to do industrialized farming. So in a very real sense, every single thing you have probably ever eaten in your life was due to this industrialized farming thing, and it has been paid for at incredible cost to the atmosphere and to the environment and to the energy usage of us as a human species, we have paid an enormous cost to make that happen. But the bean plant doesn't need to heat up the two gases to 5,000 degrees and put 50 atmospheres of pressure to get ammonia, which is what we would do industrially. The bean plant, in the nodules of the bean plant, in the root of the bean plant, there are some parasitic nodules. They're not actually part of the plant itself, right? And in the nodules, there are some bacteria. And those bacteria take that nitrogenase, which is that huge protein molecule over here, and in the core of that protein molecule is this Femoko thing. And that catalyzes a very low energy way of forming ammonia. This is happening in nature, right? But we don't understand how. Because if we had to try and figure out how the Femoko thing actually worked, we can't analyze it computationally. We don't have the computational resources on this planet to do that. So if we could now find a way to take that problem, represent it in a way that quantum mechanical phenomena can actually find a solution for us, we may be able to find better ways to do nitrogen fixation at room temperature and dispense with the Bosch-Haber process. That's $1 trillion problem. It has profound implications on humanity, right? Because it's not a question of haves versus have-nots anymore. To make energy, to make fertilizer, you need energy. If you don't have energy, you can't make fertilizer. That changes the equation. So there's profound impact from being able to solve this problem. So this is an example of the kind of key area that you can actually apply quantum computing to, right? We'll come back to this problem in a bit. You'll be interested to see what it actually takes to make it happen. But fundamentally, the first step in trying to solve a quantum application is to find an algorithm that actually demonstrates a speedup. And this is not easy to do. There are literally a couple of dozen algorithms that show any speedup at all. For the vast majority of current problems that we have, most of them cannot actually be sped up with a quantum computer. But some very key ones can be. Once we do that, we can actually simulate using mathematics, some kinds of mathematics. You can simulate that you can get the speed up, and you can also simulate how to optimize the algorithm in such a way that when you do have a quantum computer, you don't need as big a quantum computer as much time to actually solve the problem. And this we can start doing now. So if you want to look at what the state of the art is, the people are very, very assiduously working on finding new algorithms, but that is quite rare to come by. Most people are actually taking up quantum algorithms that are already there and studying how they work and studying how to speed them up. And when we go into talking about the development kit that Microsoft has put together from the team that I work in, we have simulators that can actually help you characterize an algorithm that you've come up with and find ways to actually improve upon it. So this is, in fact, the state of the art at the moment. And here is an example of how we put that into place. So if you look at a Femoko, classically it would be something like 3.5 billion years to solve that problem. The first quantum computer that we modeled, and we took the algorithm, and then we did a counting operation on it, just ran a profiling mechanism on it, and said, OK, here's how we would model it. This is how many gates we would need. That is, a gate is a single operation on a qubit, and how many of these would we need, how many operations would we need over time, and it improves it somewhat. I mean, it moves from about 3.5 billion years or something to 30,000 years. It's a huge improvement. I would say not as useful as we would like, right? But this paper exists, right? I mean, the paper up there, you can download and take a look at it. It started at 30,000 years. And then we started applying standard software engineering optimizations on the algorithm. And by doing all of these one at a time, using the tooling that was available at the time, and the tooling that we have made available to the general public now, we're now at a position where we can bring it down to a day and a half, right? You still need a lot of qubits. As it turns out, you'll need something like 170 or so qubits, which is, as we'll find out, quite a large number, right? But that now becomes tractable. That is something we can now reach for as, hey, this is something we can aspire to get a solution for. And that's a huge and profound situation to be in. This is an exciting result. So the net result of this is that effectively, even this early into this space, even without a physical quantum device that you can actually work on, there is enormous scope for doing something with research. So researching quantum algorithms is actually very, very important, and people can start doing it now. So what does that look like? What does quantum information look like? I am going to take you through something that a lot of people would probably step back and say is kind of scary. I want you to walk away from this with one profound observation. You have already been doing most of this stuff without knowing. Right? So let's start with classical operations. Anyone familiar with the most basic operation you can do on a single bit? Right? Maybe not the most basic, second most basic, but that's a NOT gate, right? So it's an operation that takes a 0 to a 1 and a 1 to a 0. And that's all it does. It doesn't do anything else. It's as simple as that, right? At this point, everyone is probably scratching their heads and thinking back to their first year of college and wondering how you implement one of these NOT gates, right? Oh, there's a transistor somewhere, there's a presence of charge, there's an absence of charge, presence of current, absence of current, something along those lines. Everything you learned as this NOT gate being an abstraction of one of those physical properties was a sugar-coated lie. What's actually happening is mathematics. So I'm going to change what 0 and 1 look like, not as the presence or absence of some physical quantity, or the presence or absence of some signal. I'm going to change what 0 and 1 look like to be two vectors. Okay? The simplest way to think about it is the 1 is in the 0th place on the top for 0, and 1 is represented by 1 in the first place. Easy enough? Have I lost anyone? No? Good. Already, I have now lifted an abstraction away from something physical to something logical. So, what does a NOT gate look like? If a vector is representing a bit state is represented by a vector, the NOT gate is a matrix that multiplies that vector and gives you back another vector. Okay. So that yellow vector is a specially chosen one that when you multiply 0 will give you 1, and when you multiply 1 gives you 0. So with me so far? Have I lost anyone? No. See, I told you it was easy. Now I'm going to introduce one other operation because dealing with single bit is not so much fun, right? So we're going to take 2 bits and create the state of a 2-bit system. So if you think about a classical system where you have 2 bits, it's a bit string either 0, 0, that means both the bits are 0, 0, 1, that means one bit is 1 and the other one 0, 1, 1, so on. You're familiar with the bit string part of it. I'm just showing you what that operation looks like from a vector's point of view. All right? Now, if you actually squint kind of hard on this, you'll realize that I'm multiplying 0 and 0. And it shouldn't come as a huge surprise to you that that vector on the furthest right is actually 0 as well. You want, right? So 0 times 0 is still giving you 0. We should be all very comfortable with that. Right? One thing that should start alarming you now is, hey, I need double the number of numbers to actually represent the state of 2 bits. So if I do 3 bits, I'm going to need 8 times the number. So you're now exponentially growing the size of the vector space that you're going to be operating in. But there are only a couple of vectors that you can actually represent in that space. Because 0 times 0 is still giving you 0, but now that 0 is a 3-bit 0, right? So before everybody goes glazed over and I start like filling the place with ones and zeros and then force you to count and all of that, I'm going to introduce a sort of shorthand notation. So we're going to take the first one, which is the vector. I'm going to call it that notation at the side over there. And if you think about what we're doing, the ket 0, which is the symbol that you have there, the pipe and the 0, that label represents the 0 bit, and the ket 1 represents the 1 bit. And now when you tensor the thing, you get a bit string. And now we're back to comfortable, familiar land. Because if you see 0, 1, 0, it means the second bit is 1. Right? So the bit string piece now is what you've seen so far as, oh, this is what happens when I put 4 bits together. I get like 0, 1, 0, 1. Right? But what's actually happening is it's a vector in a very high dimensional space with that label. That's the only change. It's not a value, it's a vector somewhere. Okay? How many people have I lost so far? I'm beginning to lose people. Okay. Hold on to your hats. Because this one's a little complex. Everyone who's dealt with numbers so far has dealt with the number line, right? I don't know when they teach you about number lines here, but I learned about it when I was first grade or something. You know, there's 0 in the middle, there's 1, 2, 3, all the way to infinity, -1, -2, -3, all the way to minus infinity. Every number that we know of and that we commonly interact with falls somewhere on this number line. Pi is somewhere over there, E is somewhere over here, right? And so this number line we're all comfortable with. Fair? Where it starts getting interesting is when we want to actually represent a complex number. And this is one concept that actually changes the equation a little bit. And a complex number, if you think about it, doesn't put a number just on this line, but imagines another axis this way with I. So I, 2i, 3i, 4i, minus I, minus 2i, minus 3i, and so on. So a point over here is so many times on the real axis plus so many times on the complex axis. You with me so far? I haven't lost you? So let's rewrite the familiar number that we know of as just a complex number. So that 0 vector now is not a vector in real space, it's a vector in complex space, okay? But it happens to lie on the real line. So there's no complex component to it. And 1 is also on the complex line. I mean, it's on the real line, has no complex component. And the vector still stays the same, right? But now if you think about what does it look like to draw one of these things out, because I went from showing you a point on a two-dimensional plane, right? 0 and 1 are 2 points on a line now. But I made them effectively 2 points on a plane. They just happen to be on the same line, right? What happens to every other point on this? There's actually 4 dimensions you need to show now, right? Now let's, 4 dimensions is a little hard to draw. So we'll project it into 3-dimensional space and pretend like the 4 dimensions are effectively on a sphere. So every point on the sphere represents 2 complex numbers. And so your real line effectively is your north and south pole. So 0 is at the top, 1 is at the bottom. And somewhere in the equator you have other points, right? Which have both 0 and 1 components, just like in the plane, but this is now a 4-dimensional thing, right? And if you think about a beach ball, you're still, all I've done is I've taken your real line with the 2 points. I've made this a plane, there's nothing else on it, and now I've represented this as a sort of beach ball with the north and south pole being the 2 points that you're familiar with. That's all I've done so far. All of classical computing involves just these 2 points. So when you want to do a knot, you rotate the beach ball so that what used to be the north goes to the south, what used to be the south goes to the north. So point is either on the north pole or the south pole, and your entire classical computation is just that. The mind-blowing moment is, what if I added every other point on the sphere? Then every operation on this is still a rotation of the sphere, because if I had a big beach ball over here, and I really should have brought one, and I took a marker and I put a dot on it, and there's only one way to get from any point on the sphere to any other point on the sphere, is to rotate the sphere around. So every value that this system can take is just a series or a sequence of rotations. In fact, rotation is the only thing that you can do to the sphere, because you can't change the size of the sphere, right? And here is the beautiful part. That is, in fact, what a qubit is. That's quantum computing. Is when I say, I'm not just interested in the north and south pole, give me all the other points. And now all the operations I can do are exactly the same as the ones I used to do before, except before I only had one rotation, which is the flip one. Now I have other rotations that go halfway, or so many degrees, or this followed by that. So I rotate in one direction and then rotate by another axis, and I'm now on another point on the sphere. So one thing has not changed, right? The size of the sphere hasn't changed. So if you write your state, which is that weird Greek symbol, remember that 0, 1 were just labels, right? So I'm now giving this a label. So size a label. It has 2 components. There's an alpha and a beta. So it's not just 0 and 1 and 0. It's alpha and beta, so any points on that sphere. And you can decompose that as effectively so many times the 0 vector plus so many times the 1 vector. OK? Haven't lost anybody so far. The sphere's size stays the same, so the vector must stay on the skin of the sphere. That's what that is. And alpha and beta are both complex, right? This now represents all qubit states. So all of quantum mechanics is just that. We took classical mechanics, and we just extended it a bit, and we're here. So you've been doing quantum mechanics all this while. You've been doing quantum computing all this while. Granted that the only thing that you did so far was use that X transform. That's the only thing you were allowed to use, so you used it. Now I've got a whole bunch of other transforms in there. And so the algorithms associated with actually manipulating the state of a qubit involve sequences of these operations. Each of these operations, just like I showed you the NOT gate, as being equivalent to the X transform. Each of these transforms are called gates as well for precisely that reason. So you have an X gate followed by something, and that puts your dot in a position that you want. And you have an infinite number of dots. And with a finite number of transformations, rotations, you can get to any place on that sphere by just starting at the North Pole and making a finite number of transformations to get within epsilon of that dot, right? So obviously, to get to use quantum mechanics or use quantum computing, you need to have a little bit more. Everybody has a great intuition for what NOT does, and they're able to build out the entire calculus of classical computation using just those operations. You can extend NOT, and then you get AND, and then from AND you get NAND, and then you have this theorem that says for any n-bit value, all circuits can be implemented with a finite number of NAND gates. And now, effectively, Tetris or Facebook is one very large NAND gate circuit. Okay? That's not as absurd as it sounds, because that's exactly what you're doing here as well for quantum computing. It's just that you have to have intuition for more than one gate. You can actually do a lot more with that, right? There's one interesting catch, though, which I will tell you in a minute. Anyway, so we've seen the matrix representation of a NOT gate, and it does exactly that. That's how it works. I'm going to introduce one more gate, which is the Hadamard gate, and it takes the North Pole and sticks it on the equator. Okay? And this is the catch in this problem. Because you can store an infinite because you can store an infinite variety of values in a qubit, you have the ability to expand the space of computation from just the North and South Pole, right? So a single operation now I can actually operate on a lot of values, right? Where nature draws the line is when you ask the qubit, where is the dot? And nature will tell you it is at the North Pole or the South Pole relative to the probability of where the dot is. It won't tell you the exact location of the dot. And that is actually the problem of, well, it's the phenomenon that people look at and they say observation causes collapse. That's what that means. So even though you have this, nature has this huge, rich notebook where they can write values down that you can't see, when you ask nature to tell you where it is, it probabilistically collapses it to either a 0 or a 1 and gives you back one classical bit of information. So this is what makes the quantum computing piece hard, because you now have to represent your problem in a way that allows you to operate on these values that you can't actually manipulate. I mean, you can't actually view, but you can manipulate, right? How many people attended Mark's talk this morning about monads? Okay, this is a physical monad. This is, in fact, a physical monad that will not let you look inside and extract the value. There is no way to pull the value out of the monad. So the question that Mark asked, how do I get the value out of the monad? Well, if it's a qubit, you'll get a value. It won't be the value you thought you had. It'll be either 0 or 1 probability-based. But the value of the monad, you can inject behavior into it and do the rotations. In fact, that Hadamard rotation is you telling the qubit, please spin yourself in such a way that a dot on the North Pole would have showed up on the equator. And then the next operation will ask the qubit to make another transformation. You do that transformation, and you land the dot somewhere else. And you compute these values in such a way that when you ask the results, probabilistically, the correct result shows up near where you expect it to be. And in a very real sense, that sequence of instructions that you gave the qubit to get to that point, that is a monadic sequence to a quantum state monad that physically does not let you violate the no-looking rule. Okay, so from a functional programming perspective, that's how it's easy to understand what's going on. All right, so anyway, superposition is one of these, and why is this important? Because from the equator, is it more probable to get back to 0 or 1? No. It's equally probable. It is, in fact, a quantum coin flip. So if I wanted to generate a sequence of random zeros and ones, I would take a qubit in the 0 state, apply the Hadamard to move it into superposition, and then measure it. And nature will sometimes give me a 0 and sometimes give me a 1 with equal probability. And from a quantum perspective, I get perfect quantum randomness. Right? That's the simplest application, in fact, of a single qubit. Now, there are other operations that I can tell you about that go around entangling and teleportation and all of that, but we will stop here with the quantum information, and we'll come back to an interesting observation. Let's go back to this number for a second here. You see how every time I added a vector to this equation and tensored it in, it doubled the state space? That puts a clamp on how much I can actually write down classically, right? Everyone's famous with this thing, the example of the chessboard. So it turns out 30 qubits my laptop can handle within my lifetime, within the lifetime of the sandwich I'm eating, right? 40 qubits, you need about 16 terabytes. You can get that in the cloud. If you throw enough money at the problem, you can kind of manage to simulate 40 qubits. But remember now that every operation on 40 qubits is also a 2 to the 40 by 2 to the 40 matrix running on a 2 to the 40 vector. So it might take some time, right? 50 qubits is currently beyond the reach of existing computing. 260 qubits, and you cross the number of atoms in the known universe, right? So you remember the Femoco thing where I told you you need like 100 and something qubits? 2 to the 150 is kind of roughly the number of atoms in the planet. So if your entire planet was treated like the RAM portion of a computer, where every atom on the planet was addressable as a RAM cell, you couldn't write down the problem for Femoco. So this should give you a sense of the scale of the problem that you're trying to solve. So obviously, flipping the problem around, you only need 260 qubits, or you need only 100 and something qubits, 70 qubits or so, to solve the problem that you can't even write down with 2 to the 150 atoms, right? So it's easier to get the 170 qubits, actually. And we're hoping that that's the case. So how do we go about doing 170 qubits? How many qubits do we have right now? In round figures, none. Nobody has a qubit, right? People have qubits, and we'll come to what that means in a minute. Like IBM has devices that actually show qubit-like behavior. So does Google, and so do we, right? But real qubits, and there's a difference between all qubits not being created equal and logical and physical qubits, we are actually not quite there yet. So let me tell you a story about this guy. So in about 1937, this Italian gentleman predicted mathematically the existence of a quasi-particle that effectively represented a split electron. So if you think of a half electron, in that sense. Let's come back and talk about quasi-particles later. I won't get into the deep details right now, but I'll give you the general hand-wavy solution, right? So if you think about an electron, right, what is an electron? It has a bunch of things, like it has many quantum numbers. Well, let's consider just the spin of the electron. Let's say we have the electron spinning in one direction. What happens when you have a whole ton of these electrons around the place? Well, they kind of start interfering with each other. And so if your information is encoded in the first electron spinning in one direction, it's going to start getting affected by all the electrons around it. This is quantum noise. And this causes the spin to actually degenerate. So you may start out in one state, but after interacting with a few million electrons in a few millionths of a second, that spin is lost. That information is leaked, and you lose that information. All right? As long as the spin is either up or down, we can treat it like a two-level system, and we can build qubit-like abstractions on top of it. But the trick is to try and find a way to keep the spin from not actually being lost. And one way to do that is to line up these things like a train. So if you take all the electrons and line them up so that the spin is the way you want it to be, then if you really think about it, the two ends effectively they turn this whole train into one electron, right? And that electron is extremely resistant to individual noise. So it's likely to keep its orientation for a long time, right? And this is actually the foundation of the Majoranic qubit, because when you have a series of electrons, and you can consider the electrons having a real and imaginary part, like a complex number. If you line them up in such a way that they're real and imaginary, and you apply certain kinds of fields to that system, you can set it up in such a way that they actually repair their halves. So the Majorana particles basically sort of swap partners, if you think of it like that. So you'll end up having a real part on one end, and the corresponding imaginary part maybe 10 nanometers away, which is a universe apart as far as the electron size is concerned. And now you have the ability to actually have an extremely stable particle that is actually a very heavy electron. It's got the same spin behavior as an electron, but it's too big to be impacted by the kind of interference that would have been able to flip a single electron, right? And this now becomes a two-level system that's like probably 10 to the 5 times more stable than a single electron, right? And so using this mechanism, well, first off, one of my teammates actually saw this in the lab in 2012. And in the last 6 or 7 years, we have been working very hard to actually use this mechanism to build out a qubit. And like I said, let's skip over that slide. Like I said, not all qubits are created equal. You can have a high error rate where the qubit only holds on to its state for a very, very short period of time, and try to synthesize a logical qubit from it. But in many cases, you may need 10,000 qubits in order to be able to hold the information associated with one qubit long enough for you to operate on it. Or you can go with a low error rate qubit and hold the information for longer with fewer qubits, fewer physical qubits. Ideally, what we would like, of course, is to have a large number of low error rate qubits, and now you can have a scalable computing system. And so from that perspective, it's true that none of us has actually got a stable low error rate qubit. We have some high error rate qubits in the state of the art at the moment, but nobody has enough to actually store information long enough for us to do anything useful with it. Ultimately, we will get to the point where we have enough qubits that we can start doing computations that we can't simulate, even on a cloud. And at that point, we will have moved into an arena where we have sufficient error containment and sufficient scale to be able to solve the problems. And as it turns out, the first few applications of this are actually going to be the chemistry simulation type of example that I've showed you, where we can understand complex molecules using these systems. You know, with a couple of 100 qubits, we can start solving world hunger, basically. And I think that's an extremely feasible sort of objective that we can look forward to. So what does a computer look like? What does a quantum computer look like? When will you get one to put in your pocket and carry around with you? Probably not anytime soon. That thing's not a quantum computer. It lists a very nice picture, but it's actually the case of a quantum computer. It's the thing that keeps the thing cold. So if you heard me say I want to isolate the qubit system so that we don't actually interfere with it, because anytime you interact with a qubit, you're effectively measuring parts of it, and you're like collapsing state, right? So one way to actually create isolation is to chill the thing close to absolute zero. And way down at the bottom of that thing, where it's 0.01 Kelvin, 15 millikelvin or so is where we actually keep the qubit. It's a trifle cold, right? We sit up at 300 Kelvin. I put on a sweater, so I'm relatively warm at that point. But at the top end of it, you have 300 Kelvin. At the bottom end of it, we have 15 millikelvin. And the engineering challenges of just getting all the information up and down, think about it, right? There's going to be a wire that goes to the qubit, one end of which is at 15 millikelvin, and the other one is at 4 Kelvin. And you're going to try and prevent the heat from actually going down and ruining the lower temperature. So the engineering work associated with building one of these things is phenomenal at every stage, right? But at the very top, it's easy to now think about an abstraction where we have a software logical computation model. And just as I mentioned earlier, that monadic sequence of operations that act on the qubit state is actually, in some sense, the program, right? And we want to be able to look at that program and analyze it and say, OK, why are we doing these two things next to each other? We can collapse those two, and so on and so forth, apply all kinds of classical type optimizations on top of it. And we do that by expressing that sequence in its own language. And we've implemented Microsoft Q# for doing that language. So there's a language compiler, which can then be used for doing optimization. And we built out a whole bunch of algorithms. All the quantum algorithms that are there have Q# implementations, which you can then now go and download and start operating, playing with. So we give you you write a little host program, and there's a little simulator, and you can run it either locally or you can run it in Azure. So that's the model. So the purple bit is literally your laptop, and the lower green bit basically is the Azure thing. The little calculator piece is you simulating the stuff. You're doing quantum computing using linear algebra, right? Vector math. Someday we'll have a quantum hardware thing that actually uses quantum mechanics to do the math. And it should be faster, and it should be bigger than we can possibly achieve with the simulator. But this is what is going to happen. Now, what was I going to say? Yes, because the exotic hardware that you require for running this stuff and the exotic environment, of having a fridge and sort of a high maintenance device and all of these things, the logical approach to actually make computation available is to effectively treat the quantum computer as a remote cloud-based coprocessor. So that's, in some sense, how you should think about writing Q# programs. So when you start using Q# to do stuff, there's always going to be something that runs classically that delegates the quantum piece to something that runs the quantum operations, right? And so I'm going to just give you the blurb on the quantum development kit. So there's the language. There's a whole bunch of development tools that you can download and try on. There's the simulator that we provide, multiple simulators. We have one that does just counting, so you can estimate how much resources your algorithm will take if you had to run it, and you can optimize your algorithms that way. And then you have all the libraries and samples that are available. And this stuff is freely available. It runs, it's completely cross-platform. You can download it, and I will give you the links later. But I have 5 more minutes, and it is going to be my pleasure to show you some quantum weirdness. So we have met this guy, right? And it takes a state, it puts it into superposition, right? And then when you measure something at the end of this thing, you expect to get, if I started with 0, I expect to get 0 or 1. So let's say I run this 1,000 times, I expect to get sort of a half and half kind of an environment, right? So I'll show you what the Q-sharp code looks like. This should be, everyone can see the code, yeah? Or do you want me to make it bigger? Is this cool? All right. So this is effectively the host program, the run weirdness test. Effectively, all it does is we're going to run single Hadamard first, 2 Hadamards, one after the other, and then 2 Hadamards with a measure in between, right? And I'll show you what that code looks like. So there's a single Hadamard test. This is, in fact, the quantum weirdness wrapper. But the single Hadamard is very simple, 2 lines of code, right? H, and then measure. The double Hadamard is H, and measure. And the third one is H, measure and throw away the measurement. Just look at the thing and throw it away. And then measure it again. Or Hadamard it again and then measure it, right? Now, what would people expect from the first one? The first one is fairly straightforward, right? You basically, let's see. I'm just going to .NET run this because, can everybody see that? So if I started with 1,000 times and my initial state was false, I get 494, 506, 473, 527. It's not really a loaded coin. It looks pretty random, right? Now, think about the Hadamard and a flipped coin. And what happens if I do the Hadamard twice? Like, what happens if I flip a flipped coin? This is where intuition doesn't actually help you. Because as it turns out, if you do a Hadamard and then you follow it up with another Hadamard, it doesn't matter what happened in between. The second Hadamard undoes the first one, without knowing what result came in the first place. So the second Hadamard effectively unflips the coin, right? And we can run that and check. And if I start with 1,000 falses, I get 1,000 falses. And if I start with 1,000 truths, I get 1,000 truths, right? Now, I'm going to measure in between. So I'm going to start with Hadamard, and this is why quantum debuggers will not work. Because if you put a breakpoint to see what the value is, you might actually change it, right? So this is me doing the breakpoint, right? I'm measuring it just to see what the value is, and then just continuing on my merry way. What do you think happens? And there you are. You, sir, are 2 quantum computer scientists already. We go back to being half and half. So, of course, he doesn't believe that all I'm doing is the. So I'm doing a Hadamard, I'm measuring and ignoring the value. I'm not using ignored anywhere. And then I'm doing a Hadamard again. But the act of measurement in the middle collapsed the state of the wave function to effectively a 0 or a 1, right? And now it's back to, hey, okay, I'm at a 0 or a 1, so I'm going to get back a 0 or a 1. And if you think about it from that perspective, it's not so weird after all, but it is actually quite a neat demo, I think, right? So the rest of the presentation is us doing that. So with that, I'm done. I have 1 minute for one question, maybe, and then you can come and catch me before you run away. Yes, sir?
How confident are you that we will actually be able to build these machines in the end? I mean, we're quite far from it.
Okay, so the question is, how confident am I that we're actually building these machines or going to build one? Very confident. In fact, that is my daily job. I work with the people who are trying to find the qubit, and it's my job to actually give them infrastructure and help them to actually find the physical device. So there's actually, obviously this stuff is not semiconductors and silicon. This stuff is, you have to find exotic materials that behave appropriately at 15 millikelvin, right? So there's a whole bunch of discovery and research that goes into it. So there's materials, there's the fabrication of the actual thing, there's actually trying to build the qubit and so on. And all of that work is feverishly ongoing. So we are obviously betting that this thing is we'll eventually get a qubit. When will we get 1,000 qubits? I have no idea. The fight to get a single qubit with the Majorana fermion has effectively gone from observing the thing and showing that such a thing exists in 2012 to possibly within 10 years of that, creating a real device that leverages that particle to build something. So that in itself is an extraordinary pace of achievement. But I have no idea how that curve, what the trajectory of that curve is. Well, thank you very much. Thank you for attending NDC. Thank you.